At 13:16 on July 24, 1994, a single alarm sounded in the control room of the Milford Haven Refinery. 11 minutes later, 274 more would join it. This is the forensic record of an alarm flood, a cognitive attack on human operators that led to a 4-ton explosion and rewrote industrial safety forever. July 24, 1994, 13:16 hours. The Texaco Refinery at Milford Haven, Wales, stretched across 115 hectares of coastline. At its centre, the fluid catalytic cracking unit processed crude oil into gasoline and lighter hydrocarbons. 8 operators worked the day shift. The weather outside was unstable, thunderstorms moving across Pembrokeshire. At 13:16, the electrical disturbance began. Lightning struck somewhere in the distribution network. The plant experienced a voltage dip, not a complete power loss, just a flicker. Enough to trigger automated safety protocols across multiple units. The FCCU system registered the anomaly. Control logic began executing pre-programmed shutdown sequences. Pumps stuttered, valves repositioned, process conditions shifted outside normal parameters. The first alarm lit up on the distributed control system console. Then the second. The operators moved to their stations. This wasn't panic, this was procedure. Electrical transients happened. The protocol was clear. Stabilize the FCCU manually, assess the disturbance, prevent a full unit shutdown. Shutting down and restarting a catalytic cracker cost days of lost production and carried its own risks. The directive from management was explicit. Keep the unit running if operationally possible. What the operators saw on their screens was a representation of the plant, color-coded graphics, flow diagrams, digital readouts. The interface told them the debutanizer, a critical distillation column, was operating within acceptable limits. Feed was entering, product was leaving. The level control valve on the outlet showed green, open position, normal flow. The physical reality inside the machinery was different. The level control valve had failed closed during the electrical transient. The distributed control system did not register this mechanical failure. The valve position indicator remained locked on its last known state, open. This was not a software error. This was a hardware fault in the instrumentation loop itself. The system believed its own false data. Hydrocarbon liquid continued pumping into the debutanizer vessel at normal rate. The outlet valve, despite what the screen indicated, was shut. Liquid level inside the column began rising. Pressure began building. The process fluid had nowhere to go except up into pipes designed only for vapor relief, not liquid surge. The operators saw green. The column saw rising pressure and liquid intrusion into its vapor relief system. At 13:18, the third alarm sounded, then the fourth. The divergence between system perception and physical reality had begun. Every decision the operators made from this point forward would be based on instruments that were lying to them. They were competent, they were trained. They were being systematically deceived by the tools designed to protect them. By 13:20, 12 alarms were active. The operators began troubleshooting. They acknowledged warnings. They adjusted set points. They cross-referenced process values. Standard cognitive load for an upset condition. Manageable. Routine, even. The debutanizer kept filling. 13:20. 31 alarms now active across the FCCU control panels. The operators split tasks. One focused on electrical system recovery. Another monitored catalyst regeneration. A third tracked the debutanizer and its associated relief systems. Division of labor. Textbook crisis management, but the cognitive model they were operating under was wrong. They believed the debutanizer outlet valve was open because the system told them it was open. The graphic on the screen showed flow. The valve status indicator showed green. There was no reason to doubt it. Instrumentation doesn't lie. That's the foundational assumption of modern process control. When an operator sees a valve indication, they trust it. They have to. A refinery has thousands of valves. You cannot physically verify each one. This trust was the vulnerability. The liquid level inside the debutanizer had now risen above the normal operating range. It had entered the vapor space at the top of the column. It was now pushing into the relief piping. The flare system designed to vent excess vapor safely during upsets, not to handle liquid surges. The flare drum, a large vessel designed to separate vapor from any entrained liquid before combustion, was receiving material it was never engineered to process at this rate. The operators saw pressure readings climbing. They saw temperature anomalies. They saw secondary alarms indicating downstream disturbances. What they did not see, what the system could not tell them, was that the root cause was a single closed valve upstream, masked by false instrumentation. They began adjusting other parameters. reducing feed rate to the column, tweaking pressure control loops, attempting to stabilize symptoms without identifying the disease. Every action was logical. Every action was based on incomplete data. Every action failed to address the actual problem. 1324. 63 alarms active. The audible alarm horn in the control room was now sounding continuously. Operators were acknowledging alarms as fast as they appeared, trying to clear the board, trying to see the critical signals beneath the noise. Alarm acknowledgement is a manual action. Each one requires a button press. Each one interrupts the cognitive flow needed for diagnosis. The debutanizer relief valve, a mechanical safety device designed to open at a specific pressure threshold, lifted. It did exactly what it was supposed to do. It vented the rising pressure, but the material being vented was not pure vapor. It was a mixture. Liquid hydrocarbon was now entering the flare system in quantities far exceeding design capacity. The flare drum began filling. Its level indicator triggered an alarm. The operators saw it. They categorized it as a secondary effect of the electrical upset, not the primary threat, just another symptom in a growing list. They were correct that it was a secondary effect. They were wrong about its priority. At 1325, the flare drum exceeded its liquid handling capacity. The overflow, 20 tons of volatile hydrocarbon, began forcing its way through the relief piping. The pipes were not rated for this. They were designed for vapor flow, not liquid mass and pressure surge. Structural failure was now inevitable. But in the control room, the operators were still troubleshooting alarms, still trying to prevent a full FCCU shutdown, still trusting that the debutanizer outlet valve indicator showing green meant the valve was actually open. The system they trusted was manufacturing their blindness. 1326. 112 alarms. The control room was no longer a workspace. It had become an environment of sustained cognitive assault. The alarm horn, a piercing tone designed to ensure attention, had been blaring for over 4 minutes without pause. Visual alarm indicators covered the console displays in overlapping layers. Red, yellow, flashing, static. Prioritization was impossible. Every alarm demanded acknowledgement. Every alarm interrupted focus. This is alarm flooding, not a metaphor. A measurable phenomenon in human factors engineering. When alarm rates exceed 10 per minute, operator effectiveness begins to degrade. When rates exceed 30 per minute, situational awareness collapses. The operators at Milford Haven were facing an average of 25 alarms per minute. Their task was not to diagnose a problem. Their task was to survive an information overload event, while simultaneously attempting to diagnose a problem. The distributed control system was functioning exactly as designed. It detected abnormal conditions. It generated alarms. It presented them to the operators. What it did not do, what it was never designed to do, was distinguish between critical warnings and routine notifications. A high-priority alarm indicating imminent catastrophic failure appeared identical to a low-priority alarm indicating a minor sensor deviation. Same color, same sound. Same urgency. The operator's brain had to make that distinction. Under time pressure. With incomplete data, while physically assaulted by noise. 1327. 141 alarms. The operators stopped trying to acknowledge every one. Impossible. They began scanning for patterns, looking for the common thread, the upstream cause that would explain the cascade. This is the correct strategy. It's taught in training. Find the root, fix the root, the symptoms resolve. But the root cause was invisible, hidden behind a green light on a screen that said a valve was open when the valve was closed. The pressure in the debutanizer relief system was now exceeding structural limits. The piping downstream of the flare drum, 4-inch diameter carbon steel, was experiencing stress. Loading it was never designed to bear. Liquid hydrocarbons are heavy. When pressurized and moving at high velocity, they exert forces that vapor flow does not. The pipe supports began flexing. Weld joints began straining. At the same moment, the operators were looking at a screen that told them flow was normal, pressure was elevated, but manageable, and the primary outlet path was clear. Cognitive dissonance is the psychological term. When observed reality contradicts trusted data, the human mind struggles. The operators had no reason to disbelieve the valve indicator. They had every reason to trust it. It had worked correctly for years. The maintenance logs showed no issues. The calibration was current. The instrumentation had simply failed in a way that provided false confidence instead of obvious error. If the indicator had gone blank or shown a fault, the operators would have investigated immediately. Instead, it showed normal, and normal is invisible. 13. 203 alarms. The last 3 minutes had generated 62 new warnings. The control room was no longer managing a plant upset. It was drowning in data. The operator's physiology was responding to sustained stress. elevated heart rate, tunnel vision, decision fatigue. These are not psychological weaknesses. These are documented human factors responses to alarm flooding conditions. The ability to detect a weak signal in a field of noise degrades exponentially as the noise increases. By 1328, the operators were in pure reaction mode. Acknowledge. Scan. Acknowledge. Scan. The higher-order cognitive function required for root cause analysis had been suppressed by the sheer volume of immediate demands, and somewhere in that flood of 203 alarms was the one that mattered. The one that indicated the flare system was receiving liquid, the one that, if recognized and acted upon, might have allowed an emergency shutdown before structural failure. It was there, logged in the system, time-stamped, recorded in the forensic data. No human being could have found it in time. 13:27 and 43 seconds. The 4-inch flare header pipe failed. Catastrophic structural rupture at a support point 110 meters from the main FCCU column. The failure mode was ductile tearing. The metal bent, stretched and split along a longitudinal seam. The failure was not explosive. It was mechanical surrender under unsustainable load. 20 tons of liquid hydrocarbon vented through the breach in under 30 seconds. The liquid was a mixture: butane, propane, pentane, light naphtha, all with boiling points below ambient temperature. The instant the pressure dropped, the liquid began flashing to vapor. A phase change, liquid to gas. Expansion ratio, 1 to 250. 20 tons of liquid became 5,000 cubic meters of vapor in seconds. The vapor was heavier than air. It didn't rise, it pooled. It spread, it flowed across the refinery ground like an invisible liquid, following terrain contours, filling low points, advancing silently in all directions from the rupture point. No flame, no sound, just a drifting cloud of molecules waiting for ignition energy. In the control room, the operators saw catastrophic system failure indicators appear simultaneously across multiple panels: pressure loss, flow loss, level excursions. The screen told them the FCCU had experienced a major upset. What it did not tell them, what it could not tell them, was that 20 tons of flammable material was now outside the process envelope, entirely, drifting through the facility. The emergency response protocol activated. Operators initiated full unit shutdown. Isolation valves closed, pumps stopped, feed cut. The FCCU began its emergency trip sequence, textbook response, exactly correct for what they believed was happening. The vapor cloud continued spreading, 13:29 and 18 seconds. The cloud reached an ignition source 110 meters from the release point. The forensic investigation never definitively identified the specific source: a hot surface, an electrical arc, a static discharge. At the molecular level, it didn't matter. Hydrocarbon vapor in air at stoichiometric ratio requires only millijoules of energy to ignite. The deflagration began at the cloud's perimeter and propagated inward at subsonic velocity. This was not a detonation. This was a vapor cloud explosion, a pressure wave generated by rapid combustion across a large volume. The flame front consumed the cloud in under 2 seconds. The pressure pulse radiated outward, 4 tons of TNT equivalent energy release. The blast wave shattered windows 300 meters away. It buckled steel structures. It threw debris across the refinery. The overpressure wave hit the control room, a reinforced building designed to withstand exactly this scenario. The operators inside were shielded. The glass held. The structure absorbed the shock. Outside, secondary fires ignited. Pipe racks, storage tanks, equipment already damaged by the blast, the refinery's automatic deluge systems activated. Water curtains deployed, foam systems engaged. The emergency response plan, written, drilled and rehearsed, began executing. 26 people were injured. Blast trauma, burns, lacerations from flying debris. No fatalities. The control room design, the blast-resistant construction, the emergency training, all of it worked. The humans survived. The FCCU did not. Structural damage was total. Rebuilding would take years. 13. Silence in the control room. The alarm horn had stopped. The screens showed only fault indicators now. The operators sat in shock. They had done everything right. They had followed procedures. They had tried to save the unit. And the unit had exploded anyway. The Health and Safety Executive investigation took 8 months. The final report identified no individual operator error, no procedural violation, no single decision that, if reversed, would have prevented the outcome. The operators performed to standard, they followed training, they responded appropriately to the data they were given. The data was wrong, and the system that generated the data was fundamentally misdesigned for human use. The investigation documented 4 systemic failures: alarm overload, poor alarm prioritization, inadequate control room graphics. flawed management procedures during upset conditions. These were not minor issues. These were architectural defects in the human-machine interface that governed a facility processing explosive materials at industrial scale. 275 alarms in 11 minutes is not a warning system. It is a denial of service attack on human cognition. The HSE report became a landmark document in process safety engineering. It didn't just analyze what happened at Milford Haven, it challenged the entire philosophy of alarm system design in high-hazard industries. The fundamental question it forced the industry to confront: are we designing alarm systems to inform operators, or to protect ourselves legally by documenting that we warned them? The answer, before Milford Haven, had been the latter. Post-incident, new principles emerged. Every alarm must have a defined response. High-priority alarms must be limited to what an operator can physically manage. Arm rates during upset conditions must not exceed human processing capacity. Control systems must distinguish between information and emergency. Instrumentation failures must fail, obviously not silently. These principles are now embedded in international standards: IEC 61511, EMUA 191, ISA 18.2. While nuclear accidents terrify us, basic industrial failures in high-hazard environments are a brutal wake-up call. What happened at Crystal River proves that procedural neglect can be just as lethal as radiation itself. In our next video, we will dissect another stunning case, the catastrophic structural collapse that shook modern engineering. To ensure you don't miss this deep dive, subscribe to the channel, turn on notifications, and hit the like button. Drop your thoughts in the comments below. I'll see you in the next investigation. Stay safe.